Hello. So I'm going to wait for a couple of more minutes to see if more students join. And meanwhile, if you have any specific questions, just feel free to ask while we wait. Okay, let's start, guys. So what I wanted to do was to just walk through the assignment. And as we go through the problems, just want to touch upon different things, but also just pipe in to ask questions. And let's see. The other thing is, unlike other office hours, this one I'm recording so that I can share it with other students. So just bear that in mind. Okay, so to introduce this assignment, so high level bit is there are 4 problems. 2 of them are combinational. One asks you to design a finite state machine, and the final one is a state machine with a data path. So it essentially sort of goes through combinational and sequential. For each one of these problems, we have given you starter files, which you would have downloaded. And when you download the folder, you will also see it has an extra logism file, which is a library that is of components that I created, which sort of get used in these problems at times. So it's not meant for you, it's meant for me when I grade it. Okay, you will also submit a report, and the report itself is follows a template. So what you got to do is to download or replicate the report. Just give me a moment. Yeah, so replicate the report, and it kind of walks you through the 4 tasks, and you'll have to fill it out as you go along. And then so just remember, you have to make a copy and then fill it out. So one of the changes from prior years I have done is because we are facing, I think, to be honest, there were lots of cases of other code violations. So this time I'm trying a couple of new things. One is I've explicitly listed some very specific things that you can collaborate on, discuss how to interpret a problem specification. You can also, of course, do it on Piazza. Discuss the approach to be taken in general terms, share testing strategy, and even input-output pairs that you are testing against, and share design performance, such as what area you are getting, what, and so on and so forth. Other than that, would be treated as honor code violation. And moreover, even for this stuff, if you're doing it outside Piazza, then the template kind of asks you, who did you collaborate with and what exactly did you do? So yeah, this is just that. There is an alternative that I'm offering, which is you can choose to do these problems jointly with one other student. And if so, you must submit the problem as a team. So you would notice on Gradescope, I will, once I activate that, there would be a team option. And the flip side out here is that whatever score post normalization you get, each one of you will get 75% of the score. But maybe if you are unconfident and all, then it's better than getting a very low score. So that's your choice. You will again have to declare that. So if you submit and then I detect that the solutions were corresponding to cheating, then you'll get 0 score. So just bear that in mind. Late submission, standard policy. So you would see that. So it's again plus 3 days there. This one variance. So I think originally in lecture 1 I had said it would be latest through Sunday, but I'm allowing through Monday. So 3 days would be June 12th, which is a Monday. Okay. Let's see. One of the things is that since the design component, the functionality part is auto-graded, so it's super important that you stick with the constraints we provide, and I'm going to kind of very briefly kind of describe those. Oftentimes what happens is that when we grade, it doesn't work, and then we have to go in and manually fix it. And here I'm referring not to functionality, but because you messed with the starter files in a way that the auto-grader just gives you a 0 score. If we have to do that, then we'll fix, but then we'll penalize you 20%. And so better not to fix. So I'll shortly describe what kind of things you can do and cannot do. The thing to also bear in mind is that just like when you design any system, software, hardware, mechanical, civil engineering, whatnot, it's not simply design. You also got to test it, right? I mean, otherwise, how would you know it works? So thinking about what you are going to test again and how you are going to test again. And I'm going to make some suggestions as we kind of go along there. One other thing you would notice is that in many problems, we are giving you constraints on what gates you can use, and for even more in some cases, how many of those gates you can use. And you must not violate these because this is a hard requirement. If you violate, we'll give you 0 score. Okay, so we're not going to get into partial credit at this point. So super important. Now to assist you in that process, once I activate, we will try to give you some feedback on things that we detect that you are violating. They may not be perfect, but at least some of the obvious things at the time of submission you would be able to detect. So but again, pay super close attention to this. Okay, nothing is worse than kind of getting the functionality right, and then maybe instead of a NAND gate, you didn't notice that we are limiting to NAND gates and you are using some other gates. Well, yeah, we can't. Since common to all the problems is the notion of area they're going to take, so I have given you the cost of Logisim modules that we have done. So here, for most of these gates, you can think in terms of the bit width they are operating at. In case of Logisim, like for example, when you have a NAND gate, there are 2 parameters there, right? Number of inputs and number of bits. So like for example, if you go to gate, if you go to, let's say, I don't know, let me pick NAND gate. Okay, so this NAND gate has number of inputs, right? So that tells you how many inputs, and then the data bits is telling you how many, each one of the input, how many bits it has, right? So like, let's say I can say 4. So this NAND gate here, each input is 4-bit, and there are 5 of those inputs. It's and then what the NAND gate does is for 5 inputs, 4 bits, it does a NAND of the corresponding bits in each one of the input. Okay, so that's width versus number of inputs. And we have given you the formula. W stands for the number of bits, and N stands for number of inputs where it makes sense. And S in case of multiplexer stands for how many select bits are there, right? I mean, so the multiplexer, for example, if I go to the multiplexer, multiplexer has this input which says how many select bits are there. So like for this one, select bits, right? So if I make it like select bits to be, let's say 3, then it becomes an 8 to 1 multiplexer, right? So that's the S out here. Okay. So and so forth. Problems which have finite state machine drawing, I have written a tool called GV2FSM, and what it does is it lets you, I basically use a language called GraphViz. So this is an example. So there are many tools which support this GraphViz language. And basically what it does is it lets you specify nodes and edges and so on and so forth. And what I've done is on top of the basic GraphViz language, I have created a convention by which one can express finite state machines. Okay, so in this particular case, you see a finite state machine written somewhat along the lines of what we have seen in the class. And kind of the idea is what my tool does is then it takes this file and then it does some sanity checks on it. And also it can actually even generate a logicent design, except it uses components which we don't allow you to use in the problems, but it gives you a functional design so that you can kind of use to test and compare your design against, for example. Okay, so that's a tool. Again, when the problem comes, I'm going to describe a little bit more about it. Okay, going back out here. So that's the tool, and then Logisame, just make sure that you're using version 3.8.0, which is the one which we're using in this course. Again, I have noticed at times, actually, these are usually the students who cheat, as in they try to grab stuff from old classes, not realizing that a dead giveaway is that your file is coming from some older version of the class. So I guess if you're going to cheat smartly, but also the autograder will fail if you use an older version. So be super careful on these things. Okay, so any questions thus far? Okay, if not, let's walk through the problems. So the first problem is who has more ones? I mean, that's kind of the title of the problem. But basically what we have is that we have two, there's a combinational problem. We have what I've given is in the starter file, if you look. So let's go back to the starter file for this problem. So what you will notice is that every starter file that I'm giving you will have at least two circuits. One which we call as DUT, which stands for design under test, and TB, which stands for test bench. And test bench really kind of, I put something minimal, but mostly so that you can check. If you test using it, then you can check that you have not messed with DUT in a unauthorized way. Okay, it's kind of just a basic simple sanity check. In this problem, you have two inputs A and B. They are 16-bit. There is one output D out, which is 16-bit, and there is another output A1, which is 1-bit. And what the problem asks you to do is to see if A has the number of ones in A. So like if you look at the bits of A, right, I mean, and count how many ones are there in A. If the number of ones in A is greater than or equal to the number of ones in B, then we say A1. Okay, so then A1 equal to 1. Otherwise, we say B1. So A1 or A didn't win. Okay, so A1 equal to 0. And then D out has to be A if A won, and it has to be B if A did not win. So I've given you a couple of examples. The first example, A, and this one is B, and you would see that B has more ones in it, and therefore D out is B, and A1 is equal to 0. Okay, so when you are doing this problem, I guess, let's see, sort of, you have to get the functionality right, but also the goal is to get smaller area. And the way I grade the area is we kind of compare it against, I guess, the best of my design and the best submit in the class, and then everything is relative to that. And you get, like if your area is outlandishly bad, then you get no score. But if it's within there's a band in which we give you full score, and then we kind of derate the score. Okay, and that's described in the later grading section. In this problem, we allow you to use the following gates: NOT and NAND. So what this means is you can use a multi-bit NOT, and in case of NAND, you can use a multi-input, multi-bit NAND. Okay, so like you're perfectly fine if you want to use a 5-input NAND gate with 4-bit width, for example. I guess that's a typo, so let me fix it. One important thing to note is that in case of Lorisip, it allows this option of negating the inputs. So like I could say negate yes, it puts a bubble out here. You should not do that. Super important. Don't do that, because think about it. If I'm putting this, it's no longer an AND gate, so it defeats the purpose of the problem. So super important. You just use a vanilla NAND gate. Don't attempt to mess with it, right? If I put inverters on all the inputs of this NAND gate, then it's actually functioning as an OR gate, right? Because inputs with an AND becomes an OR, and then there's already a bubble at the output, so it will cancel out. We'll end up with an OR gate, which we are not allowing, for example. So super important not to mess with the negation on the inputs. Okay, we'll basically not give you any score because you're using a disallowed gate. On wiring, so you can use those two from the gates library, right? Gates library. There's a wiring library where we allow you to use anything except things which are analog in nature. So, and you really, in a digital design, you should never need to use it. So we don't allow you to use registers. We don't allow you to use POR, which is power on reset. We don't allow you to power. We don't allow you to use ground. And we don't allow you to use transmission gate. We had seen transmission gate and actually, and also not transistor. Okay. Point is, don't use the intent behind wiring is really you should only need to use splitter. If you're using a sub-circuit, you would need to use a pin. Probe is very useful. Does anyone know what probe does? No one? Okay, so this brings me to another point. If you don't know something, please don't put things on chat, because I will not be able to read it. So Leon, much appreciated if you just speak up. Okay. I don't want to disrupt the flow of conversation. So going back out here, if you go to help, library reference, and then we are looking at wiring, you go under probe, and then you can read probe is an element that simply displays the value at a given point in the circuit. It does not interact with any other components. So kind of the idea is, let's say my circuit had this, right? I mean, something like this. Okay, just for the sake of argument. C is barfing because the bit width is 4, so I'm going to change it to 1. Okay, let's say I had this, but let's say I want to probe this thing, right? I mean, so what I can do is I can put the circuit out here, and then I can make it south facing so that it moves the pin down. Just gives a better looking circuit, and I connect it out here. And now whatever is the value on this wire gets displayed out here. So just easy for debugging. Do not, I repeat, do not use pins for this purpose. Okay, because the moment you push pins, then the behavior changes. Okay, so this is very useful. Another thing which is, while I'm at it, there is tunnel, which is very useful. Anyone knows what tunnel does? Nope. I'm going to try. So let's look at what tunnel does. Tunnel acts like a wire, but unlike a wire, the connection is not explicitly drawn. So kind of the idea is, let's say I want to connect this to this, and let's say this is far away in my design, so I don't want to kind of draw a long wire. So what tunnel does is it's kind of like a wormhole. Okay, so I can put this thing out here. By default, tunnel is 8 bits, so I'm going to change it to 1 bit, and then I'm going to make another tunnel, and I'm going to connect it there, except I'm going to make it north facing so that it looks nicer. And then I'm going to give them some name. Okay, so let's say I just call it whatever, double F. Yeah, okay, that can confuse you. So let's not use double F. How about tunnel 1? And I can call this guy tunnel 1. Okay, and that means there's an implicit connection between this, and I can have any number of tunnel ones. It's going to be like all connected together. Okay, so going back out here, why did I introduce these things? So if I go back to this task 1, so kind of the idea is that your DOT is where you're going to put this design. You must not, I repeat, must not move these pins in any shape and form. Moreover, you must not add any pins to DUT. Of course, if you're going to have a sub-circuit, let's say I decided in this particular case that I'm going to create a sub-circuit. So add circuit and whatever, sub 1, and here I can add pins, okay, because maybe I need pins out here. Okay, I'm going to give them names. And then in DUT, I can use the sub, for example. That's fine, but you must not put any pins on DUT, because if you do, the autograder will, I can assure you, will fail. Moreover, you should not move these things. Like, for example, if you change their ordering, autograder will fail, because the way Logisim works is the ordering and positioning matters when we use your circuit in our tester circuit. So don't mess with it. Okay, so going back out here, you have to design the circuit, which I'm going to remove this. Okay, and remove this circuit. Okay, so I have to design something which counts the number of ones in A, counts the number of ones in B, compares the two, and then if A has number of ones which are greater than or equal to that in B, then A1 will be 1 and D out will be A. Otherwise, D out will be B and A1 would be 0. So intuitively, as you can see, what is happening is I'll probably need some sort of a multiplexer to select between A and B based upon whatever the value of A1 is, right? If A1 is 1, then the multiplexer has to pass through A. If it is 0, it has to pass through B. So that part of the design is simple, and particularly because we do allow you a multiplexer. So that's not an issue. I think the tricky part in this problem is, how do you count number of ones? Now, if I had given you full freedom, there is actually a function out here called bit adder. And if you read what bit adder does, it does exactly this. It where is bit adder? Bit adder. This component determines how many ones are in the input and emits a total number of 1 bits. Okay, so this guy, as you can see, has 1 input. Number of data bits is 8. So how many bits do you think the output will have? If number of bits in the input is 8, how many bits do you think this one counter would have on the output? Folks, I'm going to not pursue unless you guys begin to answer a question. This is not meant to be a one-way thing. So someone needs to speak up. Otherwise, I'm going to end. This is office hours, not a lecture. So take a shot. Okay, I guess we're at a stalemate. I'll wait until someone answers. Or at least attempt to answer.
So this
Hello?
is what we're gonna use to build a complementary strand.
Hello?
So
Yeah,
number
hello.
4, this
I couldn't hear the question.
I'm
is
okay.
the strands. Yeah.
Okay. The question is that, so do you understand what this problem is asking for?
Yeah, so far.
Okay, well, can you explain it in words? What it's asking?
Well, from what I was following when you were saying earlier, we were just talking about how you're not allowed to move the pins. You went through the different tools that we could use.
Mhm.
Now was, as far as I got before my Wi-Fi started hacking strange.
Okay. Someone else take a shot? So my question again is the following, that we need to count the number of ones. If we didn't have any issue, I could have used this function called bit adder, which does precisely that. But if I look at the description, it counts how many ones are in the input. My question is that I have instantiated, now you're not allowed to use bit adder, but you can always use it to compare whether you're counting the number of bits correctly, right? So in your circuit, you can imagine that this is kind of the ground truth. Now my question is the following. This bit adder currently has 8 data bits, so its input is 8 bits. How many bits do you think is producing at the output, which is the number of bits which are 1? How many bits do you think I need at the output here if input is 8 bits?
I'd assume 3. 3 bits.
3. Okay, someone 3 is not in 3 is incorrect, so does someone else?
Wait, actually 4 bits. 4 bits, sorry.
That would be 4 bits, right? Because the number could be 8, which requires 1000. So this is going to be 4-bit, and we can kind of verify, right? I mean, if I okay, guys, I'm going to be asking on, if you want to attend these office hours, you have to interact. So I'm going to be asking individuals to answer. Okay. Otherwise, I'm going to wrap up and move on with this thing. I think you're treating it as a passive. So you see there are 4 bits out here. Of course, there's all errors. Okay. So my question out here is how many, if I count number of ones in A, how many bits would I need to represent it? So Aaron, can you answer, please?
If I was to count the number of bits in A, I need, like, if I'm, are you assuming not using a bit error?
Doesn't matter. The question is how many bits do I need to represent the number of ones in A?
It looks like there's 16, so
okay.
5.
5, good. Okay, so I need a circuit which would add up the number of ones and produce 5 bits. Again, if I were to allow this thing, then the solution would be simple, right? I can take this and sorry. I could have done this, but the challenge is that we don't allow you to use this, right? I mean, from arithmetic, you can only use adder and comparator. So your challenge is going to be figuring out. So again, if I had no constraints, I could do this, right? You will see this is going to be 5 bits, right? I can, after that, compare the two. That will give me A1, and then I can solve the problem. So really the heart of this problem is how do you implement the equivalent of bit counter, counting the number of 1 bit using the gates we are allowing. And as we've kind of seen this thing in the lecture, and as well as the discussion section, so I'll leave you guys to figure it out, but that's what you have to end up doing. So that's the crux of this problem. But what you can do is you can start by first creating a design using perhaps just this bit adder to make sure that you understand the functionality, because as you can realize, rest of the circuit will be unchanged. But then you have to figure out how to implement this thing just using the other modules we allow, particularly the adder one. Now, this is where I think you'll also see that tunnels are useful. Okay, so we talked about tunnels. So usually your circuit would be messy. So I think it's good to put it down there. But then instead of drawing wires, it becomes cleaner to just put tunnels. So like west-facing tunnel, another tunnel which goes out here. I have to make the tunnel 16 bits. This tunnel 16 bits, and give the tunnel a name. Sorry. Okay, so that way I can draw the circuit and without kind of messing things up. So anyway, these are some of the stylistic things that you could do, but the crux of this problem is number of ones, and which means creating a circuit which does what this bit adder circuit does, with bit adder component does. And you would see you have to kind of figure out, how do I count the number of ones? You can Google to see strategies, think about how you might do it in software. The only challenge out here is you have to do everything in combinational circuit, right? So you can't take multiple steps, right? It has to be a single step solution. Single step as in entirely combinational, right? So think about that, but that's what this problem is asking for. What else? We allow you need a comparator because you need to compare the count. You need a multiplexer because you need to select which one it is, and then adder, or you may need multiple adders of different bit sizes to do that counting. Okay, so that's what you have to do. Question?
Will we be penalized for points if we choose not to use one of the supply components? Like, for example, if we couldn't find a way to implement the solution using a multiplexer,
Oh, yeah,
even though it
that's
would have
right.
been more efficient.
You don't have to use everything. It's all this is saying is this is all you can use. You cannot use anything outside this, but you certainly don't have to.
Great, so first
Okay.
we're gonna be building.
Okay. Yeah. So you if you can do a design which doesn't need, like, for example, we have seen that comparator can be implemented as an adder plus some well, you can form an XOR gate using these, and then instead of using a comparator, you can just use an adder to do the comparison. You could, but I don't know why you would, but it's probably going to cost you more, but one would. So yeah, short answer, you're not required to use everything we are giving you. Okay. This is where I also wanted to, so while I have not set up the great scope for these problems yet, but what happens is I just want to show to you. So this is from last year's. This is last year's. No, this is not last year's. But this is a year before. But I just wanted to show you what happens when you kind of upload. So what happens is when you upload a file, we will kind of give you a message whether you are uploading the file as required or not. And then you'll also get some message like it's using a valid Logisim version and it's using only the allowed libraries and gates. If it doesn't, then you may get an error message which violates that. So let me see if I have an example of that. It should be up in a few days, so you can. Let me try one of the lower scoring students, let's say. But basically, if you violate, let me see if I try design assignment number 2. Let's try the student. Okay, so yeah, not able to find a bad example, but you'll if you violate the component library, you'll see a message there. Okay, so that will be kind of a giveaway. So I want to do everything I can to help you submit something at least that doesn't fail the very basic tests. Okay. So anyway, that's DA1. Now let's that's task 1. Now let's move to task 2 if there are no questions on this. So task 2 is again combinational, and this time around what is happening is that I have 3 inputs, sine, D1 and D0, using they are 7 bits each, and they represent an ASCII character. Does anyone know what is ASCII?
Isn't it the hexadecimal representation of a character, like a letter or a symbol?
Yeah, it's a bit binary representation of a of a 7-bit representation of characters, and this is what it looks like. If you have given you one of the URLs, as like multiple things all over the web, and you'd see for every character there is a decimal representation, there is a hexadecimal representation, there is an octal representation, but point is it's basically 7 bits, okay, because it goes from 0 to 127. Okay, so it's a 7-bit representation. For plus, for example, it's 2B. So you can expand 2B. So it's 0, 0, 1, 0, 1, 0, 1, 1. Okay. But since it's 7 bits, so it's 3 bits and then 4 bits. And likewise for everything, right? I mean, and a lot of these things are special characters. They don't mean anything, but like visible characters on our keyboard, kind of you see out here, you see out here, you see out here. Okay. So back to the problem, we have 3 inputs, sine, D1 and D0. Kind of the idea is that we are giving to you inputs which are 3 character inputs. Okay, they are of the form, the first character is supposed to be sine, so like plus or minus, and D1 and D0 are supposed to be decimal digits, so 0 through 9. Okay, except they are the ASCII encodings of those. And kind of the idea is that, so now if you think about it, it represents a number which could be as low as -99 and as high as 99. And of course, it may not represent a number, right? I mean, it maybe I gave you input, I don't know, XYZ, in which case it's not even a number. So we are asking you to give 2 outputs. NaN is high if the input is not a valid number. And by valid here, we will mean that sign has to be plus or minus. It can't be space or anything like that, right? I mean, so if so it has to be plus or minus. And then TC is the 2's complement value represented by that number. Okay, so for example, if it is plus 99, then the TC 7:0 would be the 2's complement representation of the number 99. And as you can imagine that this is 8 bits, so it can certainly represent the 2's complement. And if it is not a number, then we want TC 7:0 to be all F's. So that's what's given out here. That otherwise, if the string is not a valid number, and so the circuit should output that. So in this particular case, what you have to first do is you'll have to do some checks. Do you have a valid number or not? Which means you have to check for each digit and also the sign. Are they valid or not? And going with some comparison type logic. And then once everything is valid, then you are going to have to compute the 2's complement thing, right? I mean, so firstly, since I'm giving you a decimal thing, you'll have to convert into base 2. So let's say I give you the number 1448. You can think of it as 4 times 10 plus 8. So you'll have to think about how to do 4 times 10 plus 8, but I'm not giving you a multiplier. Okay, that's not an option. So you have to do multiplication by 10 without making use of a multiplier. We have seen that in the lecture. So you will, how will you multiply by 10? How will you multiply a digit? Now, let's say you now have a 4-bit digit. How would you multiply by 10? without a multiplier, obviously. Okay, don't answer, so we'll just, I will leave it to you to figure it out. It was covered in the lecture. Okay, so let's see what else is required out here. Yeah, so again, we are going to test you on correct functionality and low area. And what we are going to be submitting is your updated file for this. Okay, so again, you are going to take your DA1 task2.circ file and you're going to add your circuit using tunnels and stuff like that to just make for a clean design. Okay, any questions? Yeah, if not, let's move to the third problem. So third problem is a sequential one. And kind of the idea out here is to detect multiples of 7. So in the lecture, we had covered an example where we had created a finite state machine where bits were coming in, and kind of the idea was that we have to see if the bits that we have received thus far, if you think of that as a number, right? I mean, so every time we are getting a bit which is the new least significant bit. So when I start out, I get 1 bit. Let's say I get 0. Then I get 1 more bit. Let's say that bit was a 1, so my number is 0, 1. Then I get 1 more bit. Let's say it was again a 1, so my new number is 0, 1, 1, and so on and so forth. So my number keeps growing as we keep piling on bits, right? And kind of the idea out here is that you have to define, you have to design a sequential system which at every stage is going to output a 1 if the number received thus far, if the bits received thus far form a number which is divisible by 7. And it will going to output a 0 if it is not divisible by 7. I would urge you to look at that lecture where we had covered divide by 3, the case of 3, and the problem is in a similar way, except here there are a few more issues because we are now creating a real hardware. So let's firstly open the starter file. So start file is pretty simple. It has the 1-bit input X. It has a clock signal. Your circuit would be rising edge triggered. So I say that active edge of clock is a rising edge. You are allowed to use T flip-flops. So that's a twist. You can't use D flip-flops. So you have to think, okay, we are again the gates and stuff from the wiring. And I also actually in any of the problems you can, for testing purposes, you can use input output. Okay, and no other component is allowed. Actually, one thing I also wanted to mention, I never told you about the test bench. So let me do that for a moment. Okay, so let me open DA1 again. So this test bench is super simple here. Okay, I mean, and my only reason is that so I make a I call the design under test, which is where your circuit would go, a copy of it, and then I put these pins A, B, and D out in A1. Kind of the reason I like to do that is the following. Let's say you decide to be adventurous and you switch the pin order. You go to test bench. Oh, sorry, I made it in the wrong place. Okay, let's say in DUT, you didn't listen to me and you decided to add a pin. And let's say that pin is called X. Now, if I go to test bench, you would see that there is something new, X hanging free, and that would create issues, okay, to the tester, because it will see this as floating and so on and so forth. So, so test bench partly helps me identify things. Let's say I moved it up here. Okay, all hell breaks loose. Okay, so part of the purpose behind test bench is that my tester is going to call your DUT much like this test bench is calling you DUT. And in the tester, we would have things wired up. So if you mess with the pins of DUT, move them, rename them, whatever, all hell will break loose. So this is kind of a good way of doing things. Then the other part is how do we test in Logisim? And this is where what I would urge you to do is to look at the fact that you can, for combinational circuit, there is this notion of test vector. So read up about it in the documentation, but you can basically input a file where you can generate what for various input values, bit patterns of A and B, what should be D out and A1. And then it will test it for you and see that whether your circuit fails or not. This is only for combinational. That file you can generate using your favorite programming language because you know what the function does. So you can use Python or something to generate the file in a desired form. I'm also allowing you guys to share files on Piazza for testing purposes. Okay. So that's the purpose of TB. In every circuit, I've given you TB, but I expect that you will add stuff to it, okay, if necessary, or even create your own test bench, okay? But for combinational circuit, this should suffice. Any questions? So again, I urge you to read up on the test vector. It should be somewhere in user's guide, I think. Project option, menu reference. Similar. Yeah. Test vector. Okay. And then you can, the window of test vectors allow you to check your circuit to do okay. And then you can, why am I ending up in? Okay, you may need to just Google for it to see. It's also in the tutorials that I have given you. So let's see, there's no tutorials I have. Yeah, testing the circuit. So you can see how do we test a circuit. So think about the testing, but basically for combinational circuit, what you need to do is to try out different values of input and see whether you get the output correct. And the problem though is that you have two 16-bit inputs. That means a total of 32 bits. That means you have 4 billion input patterns. Of course, I don't expect you to, I mean, you can't humanly test those, so you have to figure out a testing strategy. Okay, back to task 3. So in task 3, we have 1-bit input X. I have another input called reset, and then I have 1-bit output called Z. And then, of course, you can add subcircuits and all. We allow you to use NOT gate, NAND gate, T flip-flop, and otherwise it's just wiring and all. So going back out here, the functionality is the following. Reset is meant to be used as a synchronous reset signal. Kind of the idea is that if at the clock edge, reset is high, then you should internally you would reset your state machine, kind of go to a start state, right? It's as if from that point on, after reset is finished, that is reset goes back to 0, then you are seeing the new bits coming in. So if you think about like let's say at one clock edge reset was high, and at the next clock edge reset is low. That means at this next clock edge is when you are seeing the first bit in this session. So you can think of like every time I reset, I'm kind of creating a new session for my circuit. Okay, so it's like right after reset, like when reset is low, I'm getting the first bit, the most significant bit of my number. Okay, and then I'll keep getting bits to the right. Then kind of the idea is what happens at reset. If reset is high at a clock edge, then the external world should see z equal to 0 at the next clock edge. So here is a more machine, so there's always a delay, right? I mean, if your state machine saw reset equal to 1 at a clock edge, then it will go into the reset state right after the clock edge, and then it will set the values, and the external world will get, at the external world also is some other sequential circuit, and it's observing the output of your state machine. So it will get to see that the effect of the change in your output at the next clock tick. Okay. And so it kind of goes into detail out here, but kind of the basic idea is that if at every clock edge, external world should see 1 if the bits you have received through the previous clock edge map to 7. My strong suggestion, do not use any asynchronous inputs in the flip-flops, because that's probably going to cause heartache for you. When it comes to testing these kind of circuits, okay, so let's look at out here. So this is where one useful feature so I've given so this is what I like to do. This is not how we will test, but this is just give you an example of what might happen. So I've created a test bench where I use a counter. Actually, let me first do another test bench, TB random. Okay, there are 2 test benches I provided in this problem. So what I do is I have a counter, which I select to decide how many bits I want to test over, right? I mean, so in this particular case, this counter is 8 bits. So its cycle is 256, and then it has this value out here. What it does is it generates for me a done signal. So after 256 cycles, it is going to generate a done signal, and that will go out here. This circuit, this circuit that you see, that one is actually coming from that M16 component library in the test bench. Okay, again, you don't need to worry about this, but I'm just describing a test bench. So what this guy is doing is it actually generates, if I kind of go into this, so it generates a 1 clock period long reset equal to 1 at power ups. Right after the circuit starts up, this funky looking circuit, it kind of generates a pulse on reset. So it kind of just resets the circuit. Going back out here, yeah, kind of the idea is I've given you this test bench, which is basically going to generate 256 random bits. Okay, this is a random number generator, and then DUT is a device under test, which would be your design. And then what I do is I take the output of this guy, and then this guy is actually from the IO library, and it is basically a TTY. TTY in computers is a terminal, so this is a little terminal, and which then works. It will show characters out here, so you can kind of easily see whether your output is correct or not. Okay, and then after 256 cycles, done would be high, and this counter actually stops counting. Okay, because the way I have set this counter is that after overflow, after it reaches count of FF, it will just stay at the value. So this is how you could also test, right? I mean, you can arrange for this thing to run for number of clock cycles, and then you can kind of examine whether you got the right value or not. Okay, so that's one example of a test bench. The second test bench kind of does something similar, except that this time around, instead of a random number, I take this counter value and I go into a ROM, and then whatever is in the ROM gets applied to X. Okay, so kind of the idea is that this way I can define my own test vector and then see whether, instead of a random one, to see whether things are working correctly or not. So a variety of ways of testing. The key point that comes up in sequential circuit is that you have to supply a sequence of inputs. You can't just apply an input, right? You have to supply a sequence of inputs. And that's why these test benches kind of work this way, that I use a counter to kind of count the cycles. And then at every cycle, I arrange for either some fixed value using a ROM or some random value using a random number generator to be fed to my circuit. And then I examine its output. So that's my testing strategy. You can come up with your own. The reason I like this thing is because then besides I can simulate, okay, I can reset simulation, I can simulate things and all. There is a timing diagram ability, okay? And okay, so sys clock is supposed to be the system clock. So we pick that, and then kind of the idea is that I can decide which signals to monitor, much like an oscilloscope in a lab. Okay, so I can decide what signals. So currently it is going to be viewing these signals, but I can decide more signals to view and all. And then there is a timing diagram where it kind of shows the timing diagram. And as you run the simulation, you kind of see the outputs out here. So oftentimes using this for debugging is very useful. So anyway, for sequential systems, these are some of the ways you can test, but common to all of them is that you have to look across multiple clock ticks to see whether the right behavior is happening or not. Otherwise, conceptually, this problem is basically something that we have covered in the class. Now, one other thing that I have to talk about is that you have to give to us the state diagram. So I talked about that, how I have created this tool, Editor. Editor is just a web editor for graph with language. I'll describe the tool shortly. So what within editor, what you do is that you can let me do the following. So GraphViz is kind of just a general language, okay, or language slash software, okay. It uses a language called dot language, actually, okay. So that's what you see out here, in which people make graphs, and they make graphs for all sort of purposes. What I did was that I basically created convention to express finite state machines using in this language. So the way it works is these things which say something equals something, these are in dot language just properties of the graph. So rank directly left right says plot the graph left to right. I can also do it up down, so it changes to up down, okay, but that's just layout. Size is 8.5. It's just saying something about the aspect ratio. So those are nothing to do with finite state machine. But then these are the important things. I can say input is X, output is Z, states are A, C, E, G. So I define the states. I can also define a reset signal, and I can also define what is the action on reset. Okay. So those kind of things, those are again passed on to the tool. Yeah, you don't see any effect on the here. Then I have to specify the start state. So exactly one start state. So we do it with this convention that the start state should be a double circle. That's the notation we are following in the class also. So this command should basically do that. And then this is your start state A. Okay, so if I change it to, let's say, C, then C becomes the start state. Okay, but let's leave it there. Doesn't matter what this precise functionality is, so don't worry about that. And then I list transitions. So I say there's a transition from A to C, and then the condition and action that we would normally put on the edge kind of goes out here. And actually, you can even put /n to kind of put things on separate lines. So like, for example, if you see out here, it can be written like this, or I can say /n and it writes like that. Let's just sort of whatever looks more elegant. So what this is saying is go from A to C whenever X is false, so not X, and the action you take is Z equal to 0. There is a way in which we can also specify actions as part of the state, but usually I find this one looks better. So if you look out here, G, so it says if X is true, stay in G, stay in G and make Z equal to 1. And if X is false, then go to C with Z equal to 0. So it's basically a state machine. So far, so good. Now, let me show you some other examples of the state machine that we have. So what I like to do is I use a text editor to sort of create my state machine and then use editor to kind of make sure that it visually looks good. So let me show an example of some other state machines. Okay, so this is one state machine, which I think is the same one that I showed. This is another state machine. Again, you see input, output. Okay, let's put this guy in editor and let's see what it looks like. So this is another state machine. They're all following this, like I said, a standard language called dot, which is used for graphs. And I have basically created this convention where input, output, states, these kind of things I kind of used to think. So you can use one of these templates and then kind of modify it for your purposes. Okay, so and now let me show you the tool. So the tool we have, with the link to which is given in the document. If you go out here, GBFSM tool, where do I give the link? Yeah, this is the tool. So I have given you, this is a document which describes what I've done. I've created a tool called GB2FSM that allows you to draw FSM state diagrams in graph ways. It's a text format to plot graphs, and our tool adopts certain conventions to represent finite state machines. Besides getting nice looking FSM diagrams, the tool also can then generate can check FSM for certain type of errors, not all, certainly not errors of functionality, but we check for syntactic errors. And then I've kind of given you some examples. So this, if you click on this link, it takes you to that folder I was showing right now, where there are certain examples. You can download them, but the main tool itself is a Google Colab notebook. I know some of the physics courses are using Colab and all. Hopefully all of you are familiar with Colab. If not, just think of it as an interactive tool that exists on the web. What you'll have to do is you'll have to make a copy of it. I think so, because I don't think it will let you edit it any shape and form, but I'm currently, so okay. So let's see. Is it? Restart, disconnect, and okay, hopefully it's working. So you basically start from the top. You have to install some packages, so we kind of install those. And you will see stuff which is like run once, that you just have to run once, and usually these sessions last for certain time. Okay, so it's installing the packages. First time you run it takes some time. It's basically running a Linux machine on Google's cloud server. Okay, so now it's done. You see the green sign. Then we again run the next one, which is import the modules. Basically, the whole thing is organized as cells, which you have to run by one by one. Next one is load some M16 FSM specific codes. We run that. So all of this run once. Now comes the time where you actually upload your file. So the way I have set it by default is it's going to ask you what file to upload. So when I do this thing, it's going to offer you this choose file. And so I'm going to choose the file and let's see. Of course, this would be whatever file you have written. So I'm just going to select this one. So it uploads it. And now I'm going to ask it to display and check the file. So we run it and it does a whole bunch of things. Okay, it checks that there is at least one state, there is a start state. So there's a whole bunch of things it does. The state machine passes all of them, and then eventually it kind of prints out what the state machine you wrote. Okay, so essentially, if you see some error out here, then there is kind of cause for trouble. After that, I can build the FSM table. And so there is a command out here called build table, and you can either let it do the state assignment, or you can specify to it that you want to do a one-hot state assignment, or you can specify your own state assignment. So I've given some comments, but here I'm just going to let it do the state assignment, and it works. It just does that state assignment. So you see X current state, Z next state. So it just created this. And now I will ask it to build the circuit. So in this particular case, it uses a ROM to kind of do it, to implement the next state logic and output logic. And then finally, I ask it to build the circuit. And then if things go well, it is going to download a file called fsm.circ. So it's asking for permission. I allow it. You will have to do the same thing. And now I have this FSM circ. And if I open it up, you see this FSM that exists out here. The state register, input, the ROM has all the logic. The advantage of something like this is you can test things as necessary. So I guess I'm down to one student. Do you have any question? I don't know who you are because it just shows the iPad.
Hey.
Yeah. Do you have any questions?
I'm just I'm on the discussion right now, so I'll just watch the record.
Oh, okay, you're just watching. Okay, that's fine.
Yeah.
Okay, cool. So task 4 is similar in flavor, except this time around, what you have to do is that again, there is a specification given, and you are receiving 3 numbers. So in this particular case, there are 3 inputs, each 16-bit, D in 1, D in 2, D in 3. Each one of them has an associated signal called go1, go2, and go3. And kind of the idea is that the go signals are pulsed high for 1 clock edge in order to tell you when corresponding D in is valid. And what your system has to do is, firstly, it has to honor reset, much like the previous circuit. And then otherwise, it has to wait for a D in 1 to come, and a D in 2 to come, and a D in 3 to come. And the external world assures you that we'll not have another D in 1 come while you are waiting for D in 2, D in 3, but they can come in any order. They can come even together. And once you have each one of these 3, you have to compute the median and then output it on D out. And also, when you are putting the answer on D out, you have to make done to be high for 1 clock tick, so that the external world knows that you are ready to go. So that's what this guy is asking. Now, both in this, in the preceding problem, there was no notion of speed, right? I mean, you were just outputting things. Here, your algorithm for computing the median will matter, how many clock cycles you take. So we care about both area and having fewer clock cycles. We have some limitations out here on how many gates you can use. So here you see you can only use 50 gates of these types. Also, we place a limitation on how many multiplexers you can use, but we allow you to use and one comparator and so on and so forth. So you have to, this problem has some more restrictions which you'll have to honor. And otherwise, same thing out here. You have to give the FSM and then give your design to us. Now, in this problem, you're designing both an FSM and a data path that you are working, that it will work with, because you have to compute the median, whereas in the previous problem, it would be just an FSM. So with that, I think I have covered all the problems. If there are any questions, then just ask on Piazza, and otherwise, hopefully this video will help. And so if no closing questions from, I guess, iPad, I'm going to stop at this point.
Thank you.
Yeah, bye.